All right, 10-2, linear regression and confidence bounds for prediction. Now, we're not going to do the confidence bounds portion of this. We're going to do simply the linear regression portion of this. We're going to learn about explanatory and response variables, the least squares criterion. We're going to use sample data to compute the least squares line, graph the least squares line, use sample data to compute the standard error of the estimate, and we're not going to do the confidence intervals part of that. So you can mark that out if you want. Confidence intervals. Okay. First of all, a couple of definitions here. The explanatory variable is the independent variable, x. Typically, the x variable is what we've called it in Algebra 1. The response variable is the dependent variable, in Algebra 1 typically called the y variable. No, it'll simply be your... Okay? Not because this is why they're named this way. But because, all right, explanatory has an x in it. The x variable, the independent variable, is the explanatory variable. And as we go through here, I'll try to indicate, kind of some other things about the explanatory versus the independent variable. All right, the least squares criterion. The line to fit the data points must be such that the sum of the squares of the vertical distances from the points to the line be made as small as possible. So the best fit line. We call it the least squares line, and the reason we call it the least squares line is the line fit to the data points must be such that the sum of the squares of the vertical distances from the points to the line be made as small as possible. And I really need this board to calibrate so that I can give you kind of the visual representation of what this means. Okay. All right, what you see there is you see a set of points, and supposedly what is the least squares line for that set of points. Okay? It does run, it looks like a reasonably good line. It runs in the same direction as the points and kind of separates the points into a top half and a bottom half. Okay? Now what this means is these dotted lines here represent the distance that the points are from the line. And really it's the directed distance, but it's the distance that the points are from the line. If we take that distance and use that as a side of a square for each of these, we create a bunch of squares that have a total area. Now, if you want to sketch them all out, you can. Don't feel that you have to, though. So each of those distances could be represented by a square, the square being having area of the distance from the point is from the line times itself. Now, if this is indeed the least squares line, then if we add up all of these areas, that's the smallest possible area we could get for those squares. And let me give you kind of something to compare it to. Now, I don't know that you necessarily want to write this down, but let me give you a line here to compare it to. Let's say instead we said, oh, this is my least squares line. Okay? If this was my least squares line, then if I took the area from, let's see here, fill line color, here we go. If I took the area of the squares here, and I picked a really obvious one that's obviously not correct. and I create all of these squares. Each of these squares has an area, so I'm going from the point to the line. Oops. We could look at the sum of the areas of these squares. Now, this one's pretty obviously not the least squares line, this red one, for a couple of reasons. First of all, it's not running in the same direction as the points. But also, if you notice, the area of these squares is definitely, the sum of those is definitely larger than the sum of the other ones. This one isn't one of them. But if I were to take over here and kind of just stack them next to each other, look at a total area of these. I'm building boxes here. Stacking boxes. Okay. Get the idea. Right? This has a total area of something. What that area is exactly, I don't know. But if this was the least squares line, this would be the smallest total area for these boxes. However, you can see that our original boxes here definitely have a smaller total area. Yes, I know. And I don't think you should do this on your homework or in your notes. I just want to give you an idea here. So what we're talking about the least squares criterion. You can see that the area of these black squares is going to be obviously less, quite a bit less than the area of the red squares. Okay. But this is the least squares criterion. The sum of the areas of these black squares is the smallest possible area. Okay? That's how we know we have the best fit line. In this case, quite a bit different than the red one. Questions about the basic idea behind the least squares line? Okay. Then let's talk about the equation. The least squares line is of the form y equals a plus bx. Now, don't ask me why statistics uses a different linear equation than algebra. I don't know. But this is the equation y equals mx plus b. Rearranged. The variables represent different things than they do in y equals mx plus b. But it's the same equation. Okay? Same form. Okay. What's b in this case? Y equals a plus bx. It's the slope, right? The coefficient on x is the slope, no matter what variable you name it. And what would a be? What's the constant term? It is a vertical shift. In terms of our lines, we typically call it the y-intercept. Right? If I plug 0 in for x, I would get a out of the equation. In other words, this is the ordered pair where x is 0, aka where it crosses the y-axis. Let's see, and some of this we don't need. Is this what? Yeah, that's what we don't need. Okay. And here's something interesting. Okay. The y-intercept is the average y value minus b times the average x value. Now, this is really something rather interesting, right? X bar is the average of the x coordinates. So you think about the points we plotted. If you took all the averages of the x coordinates, that would be x bar. And if you took the average of all the y coordinates, that would be y bar. What this really means then is that x bar comma y bar is a point on the least squares line. X bar comma y bar is a point on the least squares line. Y bar is the mean of the y values in the scatter plot, and the x bar is the mean of the x values in the scatter plot. The other stuff there that I'm not uncovering is things about calculating that least squares line computationally, which we're not going to deal with. All right. Mm-hmm. Mm-hmm. Ah. So let's take a look at an example. No, that bottom stuff you don't need. All right, the number of workers on an assembly line varies due to the level of absenteeism on any given day. In a random sample of production output from several days of work, the following data were obtained, where X is the number of workers absent from the assembly line and Y is the number of defects coming off the line. Part A, we want to draw a scatter diagram for the data. Okay, now I don't recall in here if I misspoke in here or if I just didn't say anything yesterday. I know first hour I misspoke. In terms of a break in the graph, I said we don't want to break in the graph, and we actually do if need be, or in order to get just a picture of our graph, of the values of our graph. So let's consider our X and Y values here. We want to be zoomed in on the picture as much as we can, in other words. So here's my X-axis, and my X values go from 0 to 5, so that's not going to be an issue. And my Y values go from 8 to 20, or 9 to 20. So let's see here. If we go 1, 2, 3, 4, 5, 6, 7, 8, let's see. 9 to 20 would be 11. So if I go by 1s, that won't cover it, but if I go by 2s, that will cover it. So let's start at 8 for our y-axis. Right, we'll put a break in the graph, and we'll let that bottom one be 8, and we'll go by 2s. We'll see if I can get this. 8, 10, 12, 14, 16, 18, and 20. And of course, on our y or our x scale, we'll go by 1s. 1, 2, 3, 4, 5. And you can go ahead and plot the points there. I'll go ahead and plot them as well. So 316. $5.20, 0.9, 212, and 110. Okay? And what do you think about that? High correlation, low correlation, moderate correlation, no correlation, perfect correlation? High? Yeah, I would say that's pretty high. If we try to sketch the line through there, if we try to just attempt a line through here, maybe something like that would be pretty reasonable. Okay. I didn't ask us to sketch the line or test the correlation, but we should ask ourselves, does a line reasonably approximate the data? If we have low correlation, then maybe a line is not a good idea. If there's no correlation, a line is not a good idea. Does a line approximate the data? In this case, yeah, it looks like it. It makes reasonable sense that a line would approximate the data. Now, part 2, find the mean of x, the mean of y, and b. We're going to leave out b for a little bit. We will find b here in a little bit, but not at this moment. And then find the least squares line. Okay. Then graph the least squares line on your scatter diagram. Okay. We'll plot the actual graph here in a moment. Okay. Now, you can find the mean of x and the mean of y simply by taking the values for x, adding them up, and dividing by the number of values. And for y, same thing. However, there is a way to get our calculator to do this for us. Ooh. And you are going to want your calculator to calculate the least squares line. So go ahead and pull out your calculator. And where would I enter data on my calculator? How about stat edit? Yeah, how about in the lists? Okay. So for list 1, I'll input my x values, and for my list 2, I'll input my y values. Now, it is important that you have them corresponding. So the order pair was 3, 16, and so you have the 3 and the 16 corresponding to each other in the two lists, okay, because you're going to match those up, kind of like with your paired data before. You deleted it. Here. We go in, we go second insert. It'll insert a new one, and now you can call that L1.
Oh, neato.
You want to clear. There you go. Stat edit, yep. And I would put my x's in L1 and my y's in L2. You can put them wherever you want, really, but it just makes life simpler if you put them in L1 and L2. Now is it going to be too cold in here? Uh-huh. Well, no, I would just put them in this order, because you want them to match up then with these y coordinates. Okay? Yeah, you're not going to put in just 1, 2, 3, 4, 5. You're going to put in the ones that are given there to you. All right, anybody need more time on your lists? All right. Now, what I'm going to show you here would be an alternative to graphing it out by hand. Okay, so the next couple of screens here on the calculator are not necessary for us to do in this case because we already have the points plotted. But if it didn't ask you to plot the points, you would still need to know whether or not the data was linear or reasonably linear. And so you would still need a sketch of the graph. Now, whether you do that by hand or use the calculator, either way, if the directions don't specify, I'm fine with. But you do need to do it one way or the other. Okay? I'm going to go to second y equals on my calculator. Okay? Y equals allows me to tell the calculator what equations to graph. Second y equals allows me to tell it what points to graph. Stat plot. Okay? And I'm going to select plot 1. And I want to turn that plot on. Yep. Now it will do all sorts of graphs, like, well, the first one here is a scatter plot. This is a line graph and a histogram and a box and whisker plot with or without outliers. And this is what's called a normal probability plot. Yes, sir? Yes, second y equals. And now select one of the plots by hitting enter. It doesn't matter which one, 1, 2, or 3. Yeah, the box and whisker is a little more cumbersome than what it's worth. And the histogram is definitely, kind of cumbersome. There's more settings that go into those. But for the box and whisker, what you could do is you could do the one variable stats, and it gives you the 5-number summary then. Yeah, which is all you need for a box and whisker. X list is L1 and Y list is L2. And then you can choose whichever point you want down here, the square, the cross, or the dot. I typically stick with the square simply because it's a little easier to see, unless I have tons of points. Okay? All right. Questions there? Now, we should set up our window because we also want it to tell our calculator where to graph this. We don't want it graphing from -10 to 10 and from -10 to 10. We wouldn't have a very interesting graph if we did that, right? Zoom standard, zoom 6. Okay? Oh, I've got an equation there. See if I can break that or not. I'm going to stop. There we go. Clear out that equation. Okay? And that does not really help me with my points. I could set my window manually, or the programmers for your calculator were really nice. If you go to zoom and go down to number 9, zoom stat, they will adjust your window so that all of your points are on your graph and take up the majority of your graph. Okay. So there is the points. Okay. Now, this is, these 3 slides right here from our calculator, this is really only if you don't graph it by hand. So we can tell, okay, is that linear? Does a line seem to be a good approximation? Questions there? Here? Okay, so go to the zoom button. It's the middle one at the very top. Not to be confused with the Flash's arch nemesis. And go down to zoom 9. Try second quit from just second mode. Now go to zoom. Now it should. Yeah. Okay. I think you were in like some other alternate F3 key somehow. Yeah. Did you go to zoom 9? Zoom 9. Yeah. Zoom 6 is negative 10 to 10. You've got a point where you don't have it entered correctly, though. So you'll get different data here in this case, Gary, okay? All right, let's talk about calculating the mean of the x's and the mean of the y's, okay? So after you input your data into list 1 and list 2, right, we know how to calculate averages. We go to stat calculate, right? Okay? So you can do one variable stats and calculate the x average, and you can do one variable stats and calculate the y average, or because the x's and y's have the same size, you can do 2 variable stats. And then of list 1 and list 2. Okay? Now the default on my calculator is L1 and L2 for x and y anyway. But if you have them somewhere else, you'll want to tell it what your x list is. We will. We're going to get there. We're going to do the mean of x and mean of y first, because the linear regression won't give us the mean x and mean y. So when I hit enter, it's going to give me some information here, a lot more information than I need at this point. It's going to give me x bar and then a bunch of things about the x's, like if I add up all the x values, I get 11, and if I add up the squares of the x's, I get 39. And some other stuff there. And you'll notice there's this arrow down here, which means there's even more information. So if I scroll down, it'll give me the y values. Which is kind of nice. Now, what does this mean then? I just scrolled down. I did 2 variable stats. There you go. Y bar. Okay. And then there's even more down there, but we don't really, it's just the maximum and minimums for x and y, which we don't really care about. If x bar is 2.2, it's 2.2 what? Yeah, absentees, right? Number of workers absent. So for our data, we averaged 2.2 absent workers. And what was y bar? Number of defective toys or whatever they're doing here, right? 13.4 defects. Or defects, depending on where you put the emphasis. Now, this point is really cool. The ordered pair 2.2, comma 13.4 is one of the points on my line. Not one of the data points that we had, but it is one of the points on the actual line. Let me turn this to green. color coordinate this a little bit better since I used blue on my graph already. 2.2 comma 13.3. 2.2 comma 13.3. Oh, looks like I'm pretty close here. Should be right about there. Looks like the line I drew that I estimated actually went through that point. Close to it. Questions finding x bar and y bar. Adding and dividing by the number, yeah. Okay. Now, John, the part that we are definitely going to use the calculator for is the next part. Okay. Seems a little, a little simple to be using our calculator, right? Just add them up and divide by 5. Unless you have a lot of points, then it might be simpler to do it this way. Oops, sorry. Okay. That's not the right one. Okay. All right, so how do we get our regression equation? Which b here in our directions is the slope. Okay, oops. B here is the slope. So we want the slope in the least squares line. Well, let's get the least squares line first, and then we'll get the slope from that. So let's go to stat calculate. And I'm going to scroll down here. Now, you've got a couple of options. Okay? We're looking for linear regression. Now, number 4 is linear regression of the form ax plus b. This is the form that you typically saw a line in algebra, mx plus b. They've just replaced m with a. Okay? Number 8 here is also linear regression, LINREG. This is more the form that we're dealing with in this class, a plus bx. You can use either one. Just make sure you pay attention to which form you're using. Is a your slope and b your y-intercept, or is a your y-intercept and b your slope? Okay. The textbook uses this one, so I'm going to use this one in here. Just to hopefully a little less confusion, or a little more cohesion between me and what your textbook does. Number 9 is not linear regression. Do not use 9. That's a natural log regression, not a linear regression. Okay, so if I choose number 8 here, okay, the new calculators are going to give you some prompts, right? Oops, X list, Y list. Okay. I'm going to choose linear regression. The old ones, the default is L1 and L2, so again, I don't have to type this in on my calculator because it's the default for L1 and L2. But it gives me this data. Okay. Now, if yours does not currently spit out an R squared and an R, do not worry about that. That's actually a discussion for the next section. Okay. Linear regression, and then I did L1 comma L2. Okay. If it's L1 and L2, you actually don't have to type those in at all. Okay. That's the default. But if you put them in, say, list 5 and list 6, then you would need to put in L5 comma L6. John? There's, for linear regression? Okay, so frequency list, you just leave that blank. We want each value for x and y to be counted once. Okay? And then to store the regression equation, what you can do is you can actually have it plug in the equation into like y1. So you wouldn't have to type it in then. I don't know that it's worth our time to talk about how we do that. Okay, if you want to, I'm sure you can search out on YouTube, how do I store reg or whatever. Okay, TI-84. Okay. Now, they're telling us here's the form of your equation, y equals a plus bx, where a is this and b is that. So our equation here is y equals 8.26 plus 2.34x. This is our best fit line. It's our least squares line. What's the y-intercept? 8.26, the constant term. Which means that there's another point for my graph. If I go up here and I plot the other point on the y-intercept, I want 8.26. That's about 9, so I'll go right, let's see, 8 would be here, 9 would be here, so it would be right down here. That would be approximately 8.26, which means that my line of best fit would be this line here. There's the actual best fit line in green. It passed through x bar, y bar, and it passes through my given y-intercept. Now, you have to be a little bit careful. If your y-intercept's on your other side of your break, then you need to find some other point to plot it through, because that break represents a different amount of space than the rest of the graph.
So you put it through the y-intercept, your x bar and y bar, and the endpoint.
No, just those two is fine. It happened to. It doesn't typically. Okay? Because through any 2 points, there exists exactly one line. Any 2 points on a plane. So once you have 2 points, you know what the line looks like. Make sense? All right. Questions there? Okay, now hold on, because I want to do one more thing here with this. Okay, well, it doesn't ask you for this in the directions, and so I wouldn't expect it on the homework if it didn't ask for it in the directions. I do want to talk about it because I do know it'll happen in your project. We identified the y-intercept to be 8.26. 8.26 what? Yeah, the y values were defects, right? Or defects. My Oklahoma accent showing through. Yeehaw. Okay? What's wrong, Denasia? Now, good Lutheran question. What does this mean? 8.26 defects. What does the y-intercept mean? Was 2.2 compared to 8.26? 2.2 is paired with 13.4. The y-intercept is where what happens? Where x is what? Where x is 0. So if no one is absent, if the number of absentees is 0, we expect approximately 8.26 defects. Now I don't know which way is the right way. If x is 0, if no one's absent, we expect there to be 8.26 defects. Now the other part here that we do have to do that we haven't done yet is identify the slope. What's the slope in this case? The coefficient on x. Yeah, 2.34, right? Okay, 2.34, if I wrote that as a fraction, 2.34 over 1. What does this mean? What does slope mean? It's not the average. Okay, it is the number of defect increase per worker. Okay? Now, if you think about what slope is in general, it's change in y over change in x, rise over run. So our y value was a change in the number of defects, and so if you're having a hard time with what Darian was saying, maybe this will help. Okay? A change in the number of defects divided by a change in the number of absentees. Okay. So what this means then is that for every one absentee, we expect an increase, positive 2.34. We expect an increase of 2.34 defects. For every one absentee, we expect an increase of 2.34 defects. Effective toys or whatever they're making. If no one's gone, we expect it to be 8.26 because, quite honestly, your assembly line's not perfect, even if everyone's there. There are going to be some toys that are not going to be perfect. Okay? But for every extra person that's gone, there's an increase in that. Okay? All right. So here's the plan. Your homework is due next Wednesday. Okay? Oh, wait. Sorry, no. That's the previous homework. That homework is due Wednesday. We will wrap up this section next Monday because tomorrow is homework and day of review, and then Thursday's your test, and then Friday is career day. So we'll wrap this up on Monday. This next homework will be due next Tuesday.